Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
So if you fail your road test, you do not get your driver's license.
Right.
And on the surface, that just, it just feels like common sense, right?
Totally.
But behind that really simple everyday outcome is a hidden mathematical formula. It's like this literal equation of language that dictates everything from, I don't know, winning an argument at the dinner table to how the most complex global database software functions.
Yeah, absolutely.
And usually when we talk about language, we treat it as an art form. We think about poetry or, nuance, emotion, interpretation. But today, for this deep dive, we are stripping all of that away to look at the cold, hard engineering underneath.
Yeah, we're really looking at the raw mechanics of thought here, because underneath all of our messy, highly emotional communication, there is this incredibly rigid mathematical structure that governs what is logically true and, well, what is logically false.
Right, but because we're diving into the literal math of how we construct those thoughts, we're actually switching up the dynamic today. For this deep dive, I am officially putting on my student hat.
Oh, nice.
Yeah, I'm handing the reins over to you, so you get to put on your lecturer hat, and you're going to guide us through this structural framework.
Well, I happily accept the lecture. I mean, it's a brilliant topic, and just to give credit where it is due, we are pulling our entire framework today from section 2.2 of chapter 2 from contemporary mathematics.
Which, just to keep things conversational, we'll just refer to as section 2.2 or simply the textbook from here on out.
Perfect. Sounds good. So our core mission today is to explore what the textbook calls compound statements.
Compound statements, got it.
Right. And when you understand how these statements are built, you basically unlock a kind of cheat code. You suddenly see how lawyers construct ironclad contracts or how politicians dodge questions.
Oh, they are so good at that.
They really are. And it even shows you how a computer algorithm actually processes information. And that brings us right back to your driver's license example.
Okay, yeah.
In most jurisdictions, to get that license, you have to pass a written test and you have to pass a road test.
All right, you need both parts. You can't just memorize the rule book, but be a total menace on the actual highway or, vice versa.
Exactly that. Now, consider the statement, my friend passed the written test, but they did not pass the road test. That is a classic compound statement.
Oh, okay.
It takes two completely independent thoughts, and it literally just glues them together.
Yeah.
And evaluating whether that entire compound structure is true or false based entirely on the truth of its individual parts, that's the foundational bedrock of all logical reasoning.
Okay, so as the student here, let's look at that glue. Before we start building massive, complex, logical arguments, we kind of need to understand how these independent pieces actually stick together, right? We're looking at the connective tissue.
Exactly. And in section 2.2, this connective tissue is defined as common logical connectives. So we take independent clauses, which, just as a quick refresher, are simply statements that can stand entirely on their own as a complete thought.
Right.
And we join them using very specific operations.
So these connectives are basically they're like logical circuit breakers. They determine if the current of truth gets to pass through to the end of the sentence.
Oh, I really love that framing.
Yeah.
Yeah, they are absolutely circuit breakers. So the most restrictive breaker we have is the conjunction.
Conjunction, okay.
Yeah, and in everyday English, this is usually represented by the word and or the word but. In symbolic logic, for a conjunction to evaluate as true, every single component part must be true. It demands total perfection.
Wow, okay.
And the math symbol for this is a wedge pointing up, so it kind of resembles an upside-down V or the mathematical symbol for intersection.
Yeah, the textbook uses a sports example for this, right? But if we think about it mechanically, it's pretty unforgiving.
Oh, it's very unforgiving. So the textbook uses Derek Jeter played professional baseball for the New York Yankees, and he was a shortstop.
Okay.
If we let the letter P represent the Yankees part and the letter Q represent the shortstop part, we write that symbolically as P, then that little upwards wedge symbol, then Q.
And we read that as P and Q.
Right. So if he played for the Yankees but, say, played outfield, the entire compound statement is false.
Oh, wow.
Or if he was a shortstop but played for the Mets, the whole statement is false. The circuit literally breaks unless both conditions are perfectly met.
So and just completely restricts things. It demands that absolute perfection. But, life and, frankly, language just isn't always that strict.
True.
If a contract says a freelancer will be paid if they finish the graphic design or the copywriting, they don't have to do both to trigger the payment. Surely logic has a way to represent that kind of flexibility.
It definitely does, and that brings us to the disjunction, which is the word or. The symbol for this is just a regular V shape. But we need to pause here, because this is where human language and mathematical logic really start to clash.
Uh-oh.
Yeah, section 2.2 highlights that in logic, this is an inclusive or, meaning the compound statement is logically true if at least one of the clauses is true.
Okay, let's unpack this. Because if I am at a wedding and the server asks, would you like the chicken or the fish? They definitely do not mean both.
No, they don't.
Like, if I smile and say both, I am going to get a very weird look. So why does the math default to this inclusive both option?
It is a brilliant point, and it literally causes endless confusion for people first studying logic. In casual conversation, we constantly use the exclusive, or meaning one or the other, strictly not both.
Right.
But think about how a computer or a legal system evaluates a baseline requirement. Imagine a job posting that says, applicants must have a bachelor's degree or 3 years of field experience.
Okay.
If you happen to have a bachelor's degree A&D 3 years of experience, you aren't disqualified.
Oh.
Right? You still met the baseline requirement.
Ah, I see. Because the condition is simply that at least one of the criteria has been satisfied. So having both doesn't break the rule, it just kind of over-delivers.
Precisely. Logical disjunctions always default to allowing the both scenario because it satisfies the core condition. If a lawyer or a programmer really wants to force an exclusive choice, they have to explicitly code it by writing P or Q, but not both.
Wow. Okay.
Yeah, unless that explicit exclusion is there, the V symbol always means one, the other, or both.
That makes a lot of sense. So what happens when we introduce cause and effect? Because so much of how we argue is based on predicting outcomes, right? Like, if we do this, then that will happen.
Ah, that is the conditional connective, also known as an implication. This is your classic if-then statement. The symbol is an arrow pointing to the right.
Okay.
The first part, the if part, is the hypothesis, sometimes called the antecedent. The second part, the then part, is the conclusion or consequent.
Like saying, if Pedro does his daily chores, then he can play video games.
Yes, exactly. And the best way to understand the conditional circuit breaker is to view it as a one-way promise. The logic here is actually fascinating.
How so?
Well, the only time a conditional statement is considered mathematically false is if the hypothesis happens, but the conclusion does not. So if Pedro does all his chores, but his parents still refuse to let him play the games, the promise is broken. The logic fails.
Wait, but what if Pedro doesn't do his chores, but he sneaks onto the video games anyway? Does that break the logic?
It actually doesn't.
Right there.
Seriously, because the original statement was if he does his chores, then he can play. It made absolutely no claims about what happens if he doesn't do his chores.
Oh, wow.
Maybe it's his birthday, so he gets to play regardless. In logic, if the hypothesis is false, the conditional statement as a whole is still considered true by default because the specific promise wasn't violated.
That is wild. It really exposes how many assumptions we make in everyday conversation. We just assume if-then works in both directions.
Meh.
But mathematically, it's strictly a one-way street.
Which brings us perfectly to the next connective, the biconditional. This is the two-way street. It's phrased as if and only if, and the symbol is an arrow pointing in both directions. For a biconditional to be true, both sides are locked in a permanent state of agreement. They must have the exact same truth value. If one is true, the other must be true. If one is false, the other must be false.
So to fix the Pedro situation, the parents should have said, Pedro can play video games if and only if he completes his chores.
Exactly.
That totally locks it down. No chores means no games, period.
Right, removes all those loopholes. And finally, the last piece of our toolkit is negation, which is simply the word not. The symbol is a tilde, that little squiggly line.
Got it.
Negation is unique because it doesn't join two statements together. It just sits in front of a single statement and flips its truth value. If a statement is true, negation makes it false.
All right, lecturer, I feel like I really understand the circuit breakers now. We have conjunctions demanding perfection, disjunctions allowing flexibility, conditionals making one-way promises, biconditionals locking things down, and negations flipping the switch.
Perfect summary.
But, knowing the tools isn't exactly the same as building the house. How do we take a messy, organic English sentence and translate it into clean, algebraic logic?
Yeah, that translation process is where the real work happens. You are moving from semantics, which is what a sentence means, to syntax, how it is structurally built. The textbook outlines a very specific three-step translation method.
Okay, let's apply it directly. I'm not going to ask for a list of steps. Let's just go right back to your friend with the driver's license. The sentence is, my friend passed the written test, but they did not pass the road test.
Okay, jump in. How would you approach translating that into symbolic logic?
Well, the first thing I would do is isolate the core affirmative thoughts, like the positive statements. Let's just call the written test P. So P equals my friend passed the written test. And I should probably make the second half a positive statement too, even though it has the word not in it. So let's let Q equal my friend passed the road test.
That is exactly right. You define your variables as positive affirmative statements first. Now, how do you handle the actual sentence?
Well, the sentence says they did not pass the road test. Since Q represents passing, I need to use that squiggly tilde symbol to flip it, so that back half becomes not Q.
Excellent. And the connective holding them together.
The word in the middle is but, and you mentioned earlier that but acts just like and. In logic, it requires both things to be reality.
Right.
My friend really did pass the written test, and they really did fail the road test. So I'd use the upward wedge symbol. That means the whole messy sentence translates cleanly to .p, then the and symbol, the not QP and not Q.
You did that perfectly. It strips away all the linguistic fluff, the tone, the disappointment of failing the road test, and leaves you with the pure logical structure.
It's actually deeply satisfying to distill language down like that.
Yeah.
But I do have a clarifying question, because this is, I don't know, almost too easy.
Okay, shoot.
Wait, so every single time I see the word and in an English sentence, should I just throw that upward wedge symbol in there?
You absolutely cannot. And this is where natural language processing for AI often hits a wall. Section 2.2 has a specific checkpoint warning about this exact trap.
Oh, really?
Yeah, consider the sentence. The stripes on the U.S. flag are red and white.
Okay, I see the word and right there at the end.
But look at the structure. If we try to break that into two independent statements right at the word and, what are we actually left with? The first part is the stripes on the U.S. flag are red. That is a complete independent thought. We can evaluate if that is true or false, but the second part after the and is just the word white.
I see. White is not a complete thought. It doesn't have a subject or a verb.
Exactly. It's not an independent clause. You cannot evaluate the truth value of the word white floating in a vacuum. Therefore, the sentence, the stripes on the U.S. flag are red and white, is actually just one single simple statement. It is not a compound statement. You wouldn't use the logical and symbol at all. You would just represent that entire sentence with a single variable, like S.
That is a massive distinction for you listening right now. You cannot just hunt for keywords like and or like a mindless robot. You have to look for complete thoughts. Like you have to understand the underlying grammar of the sentence before you can translate its math.
Yeah, it requires critical thinking. You are evaluating the architecture of the idea, not just doing some vocabulary matching game.
Okay, so this translation process makes sense for simple compound statements. But real arguments and legal documents are like paragraphs long.
Right.
Just like in regular math algebra, if I have a huge equation, I need parentheses to group numbers together so I know what to multiply first. Do we use parentheses in symbolic logic?
We absolutely do, and they serve the exact same function. Parentheses act as containers. They group ideas together and dictate how the logic flows. And honestly, translating symbolic logic that has parentheses back into English words is where things get really awkward. Yeah, let's expand our driver's license scenario to see why. Let P equal passed written test. Let Q equal passed road test. And let R equal received license.
Okay, we have our three variables, P, Q, and R.
Now imagine reading this formula. Open parenthesis, P and Q, close parenthesis, then the conditional right arrow pointing to R.
So what does this all mean mechanically? The parentheses are a container. They are forcing us to deal with the P and Q combination as a single unified block before we even look at R.
Yes, that entire parenthetical block forms the if part of our conditional statement. So in English, that formula translates to, if my friend passed the written test and they passed the road test, that is our grouped condition, then my friend received a driver's license.
Well, that feels natural enough. The container holds the two conditions together. But what if we need to negate that whole container? What if I want to put a not symbol completely outside the parentheses?
Now, this is where you end up sounding like a lawyer writing a terms of service agreement. Let's say we have the formula. Negation symbol, open parenthesis, P and Q, close parenthesis, implies negation symbol R.
If I just tried speaking that naturally, I might say, if my friend didn't pass the written test and the road test, But as soon as I say that out loud, I realize it's completely ambiguous.
Exactly.
Does it mean they failed both tests?
Yeah.
Or does it mean they only failed one of them?
That ambiguity is exactly why everyday language fails at complex logic.
Hmm.
Section 2.2 gives us a strict syntax rule to solve this. When an entire group inside parentheses is negated, you cannot just sprinkle the word not onto the verbs inside.
Correct.
You have to use a very specific formal phrase to indicate that the whole group is being flipped. That phrase is, it is not the case that.
Oh, I see. It is like an umbrella. The negation symbol sitting on the outside of the parentheses is an umbrella that covers every single thing inside the container. So when I translate it to spoken English, I have to, announce the umbrella first.
Announcing the umbrella is a brilliant way to conceptualize it. Yes.
Yeah.
So the mathematically precise translation of that formula becomes, if it is not the case that my friend passed the written test and the road test, then my friend did not receive a driver's license.
If it is not the case that, wow, it is incredibly clunky, no one talks like that at a party. But I completely see why it is necessary. It removes 100% of the ambiguity about what is actually being negated.
Precision is the entire goal of this system. We sacrifice poetic flow for absolute structural integrity.
All right, lecturer, I have a scenario that pushes this even further.
Bring it on.
We know how to group things with parentheses to avoid confusion. But what if someone forgets to write them? What if you are looking at a raw string of variables and symbols? In regular math, we have an order of operations like PEMDAS, where we know multiplication happens before addition, even without parentheses. Does logic have an order of operations?
It does, and it is arguably the most important rule in the textbook. It's called the dominance of connectives. It is a strict, unyielding hierarchy that tells us what to calculate first, moving from the least dominant symbol to the most dominant.
Okay, let's build the hierarchy. What's at the very bottom?
The least dominant connective, meaning the thing you evaluate first, are parentheses. Always calculate whatever is inside them first.
Makes sense, just like algebra. What is number 2?
Negation, the not symbol. It binds very tightly to whatever variable it is sitting right next to.
Number 3.
Conjunctions and disjunctions, the ands and ors. They have equal dominance to each other. If you have a string of them, you just read them from left to right.
Okay, so we've handled parentheses, negation, and the ands and ors. What is number 4?
The conditional, the if-then arrow.
Which leaves the most dominant connective, the one we evaluate absolute last.
The biconditional, the if and only if double arrow. It basically overrides everything else in the equation.
Okay, I need to know why. Why is the conditional and the biconditional at the very top of the food chain? Why do they dominate an and or an or?
Think about what they represent mathematically. An and or an or is just combining two local variables. But a conditional, and especially a biconditional, acts like an equal sign across an entire equation.
Right.
It divides the statement into a massive cause side and a massive effect side. You have to figure out the sum total of everything on the left and the sum total of everything on the right before you can evaluate if the relationship between the two halves is actually true.
That makes perfect sense. It's the grand divider. Let's say this hierarchy in action. Yeah. Walk me through a string of logic with no parentheses.
Okay, here is the expression. P and not Q implies R.
So visually that is the letter P, the upward and wedge, a tilde for not, the letter Q, the if-then right arrow, and the letter R.
Exactly. Step 1 is parentheses. There are none, so we skip it. Step 2 is negation. We scan the expression and see a not Q. Because negation is less dominant than the other symbols, it binds tightly to the Q. It gets evaluated first.
Okay.
So we isolate that not Q in our minds as one solid block.
Okay, not Q is locked in. Step 3 is ands and ors. I see an and sitting between the P and our new block.
Right. So we take the P and we conjoin it with the block we just made. We evaluate P and not Q. That entire thing now merges into a new, bigger block.
Got it. And the only symbol left is the if-then arrow, which was step 4.
Yes. The conditional arrow is the most dominant connective in this specific statement, so it evaluates last. Everything we built on the left side implies the right side. So the final structure evaluation is the block of P and not Q implies R.
So if we were to put the parentheses in at the very end, just to show our work, it would look like open parentheses P and open parentheses not Q, close parentheses arrow R.
Precisely. The dominance of connectives tells you exactly how to build those invisible parentheses. And what's fascinating here is that this is not just an abstract academic exercise to torture math students.
Yeah.
No, this exact hierarchy is literally running the modern digital world.
How so? Where does this show up outside of a textbook?
The textbook points out a real-world application that is honestly staggering when you think about it. Have you ever noticed that if you write a complex logical formula in Microsoft Excel and then you import that massive spreadsheet into Google Sheets or an Oracle database, it computes exactly the same way?
I mean, honestly, I just took that for granted. Math is math. I assumed everyone just knew how to calculate it.
But computers do not inherently know math. They only execute the logic they are programmed to execute.
Oh, right.
The reason all these competing software programs agree is because global standards organizations like OASIS and the International Organization for Standardization, or ISO, literally mandated these rules. They codified the dominance of connectives into international law for database languages.
Wow. So global tech leaders actually had to sit down in a room and legally agree, listen, everyone, not evaluates before and evaluates before if then.
They had to, because before these strict standards were universally adopted, the digital landscape was chaotic. Imagine a massive hospital system or a government agency saving a database in a proprietary software that evaluated logic slightly differently. Maybe it evaluated an or before an and.
Oh, that would be a disaster.
Complete disaster. If that software company went out of business, the hospital's data was practically useless. When a new software system tried to read the files, it would apply a different order of operations, entirely changing the outcome of the data.
Oh my gosh.
Yeah, a patient who is flagged as needs medication and deobservation or discharge could suddenly have their care instructions inverted just because the computer read the or first.
A misplaced logical priority could literally corrupt decades of preserved data.
Exactly. The standards adopted for database software maintain global data integrity. Without the dominance of connectives functioning as a universal, hard-coded law, the digital world would fracture into completely incompatible silos.
Okay, I am officially taking off my student hat. That is a phenomenal place to zoom out and look at the big picture. We started this deep dive by looking at a really simple, relatable sentence about failing a road test.
Yeah.
And by following the mechanics of that sentence, we ended up at the foundational code that keeps the global economy's databases from collapsing in on themselves.
It is quite the journey. We've taken the messy, ambiguous nature of human language with all its hidden traps like the inclusive or and the structural trickery of the word and distilled it into a rigorous, unbreakable system of symbols.
We learned the circuit breakers. We learned how to announce the umbrella when translating. We learned the strict order of operations. And for you listening, this goes way beyond passing a math class.
Absolutely.
Every time you read the terms of a rental contract, every time you click agree on a convoluted user agreement or type a formula into Excel at work, you are relying on these logical connectives and their strict dominance.
It is the unseen architectural scaffolding of our daily lives.
It really is. So I want to leave you with a final thought. Something for you to ponder the next time you find yourself in a heated debate. Whether that is in a boardroom or at a family dinner, try to do it. Try visualizing the other person's arguments as P's and Q's.
Oh, that is a fantastic cognitive exercise.
Are they actually constructing a sound logical conditional? Or are they just hiding behind the ambiguity of the English or? Are they making independent points, or are they stringing together incomplete thoughts hoping you won't notice the broken circuit? Can you spot the hidden math in your everyday conversations? Because once you see the engineering beneath the words, you just cannot unsee it. Thanks for joining us on this deep dive. We will see you next time.